Hi, John Valvano here, and in this video we're going to talk about debugging. Okay, debugging is fixing, finding errors, optimizing, documenting that our system works. And what I've told my students forever is if you learn how to debug, you're going to be the last one fired. Okay, and then once you become big boss and you have to fire people, fire the ones who don't know how to debug, whether that's hardware debugging or software debugging. This is essential. This is what makes the difference between a good engineer and a not so good engineer. Okay, so we'll divide it into two types. Performance debugging involves timing, and we talked about real-time systems. We talked about jitter. Those are the kinds of things we're going to measure. And then we have functional debugging, which is what the rest of the world does outside of embedded systems to check if I have inputs and those inputs go to outputs. Functional debugging is the ability to observe it. Okay, so like I said, we want to find, we want to improve, we want to correct, and we want to document what we're doing. And so we will develop a suite of tools that allow us to do this. Okay, and so you can distill the process debugging into two categories. One is control. Okay. Control represents what and when, not what my inputs are, what software is being run, and when my software is being run. That's the essence of control. And the second aspect is observability. Okay? Can I see what happens? Okay? And so debugging is the combination of controlling what gets run and observing what happens. All right. Some of them are sort of obvious, and we do this when we first started programming. Before we ran our first program, we typed it in and we looked at it with our eyes, and we sat at our desk and we hand executed each line of our code in our brain to see what happens. Okay, and so this is actually a formal thing where you could write down what you expect to have happen at every line of your code, and then single step the code, okay, and see what you actually got. Okay, so this is a comparison between what you expect it to happen and what does happen. And when you do this in single stepping mode, or you do this on a piece of paper, we're going to call that desk checking. And you'll see that we are going to do dynamic testing using a facility called dump, and I'll talk about that later. But let me say right now that what you've done before you got to embedded systems is a printf statement, and we're going to take out the printf statement because we got no printer, we got no console, there's no place to print it, okay? And it's bad debugging anyway in a real-time system, all right? But we're going to focus in on dumps as a software way to observe things, and we'll talk about what it is in a moment. All right, hardware. Okay, I want you to have a multimeter for measuring voltage. I want you to have a scope to measure voltage versus time. And in this slide, you can see it presents a logic analyzer. Now, sometimes we connect the logic analyzer up to pins that already exist in our system. This is part of the system I/O. Okay, and when we connect the logic analyzer or scope or multimeter up to existing systems, we're going to give that a non-intrusive, completely non-intrusive measurement for those, because it has no effect. It doesn't change the behavior at all. Other times, we're going to add some pins. We're going to add some pins that aren't part of the system. This is debugging pins. and we're going to toggle them in our software, and this debugging is going to be defined as minimally intrusive. And minimally intrusive will mean a small but measurable effect on our system. Okay, so the trace is an example of one of these non-intrusive measurements. We connected our logic analyzer up to I²C, and we sampled the clock and the data pins on I²C. Now, some of the logic analyzers are really powerful and will actually decode the protocol, whether that be UART or CAN or I²C, but this is a digital logic. This is digital, ones and zeros, as a function of time. Okay, and most scopes and logic analyzers have a very powerful way to trigger, which means to capture. And in this case here, I triggered on the falling edge of the clock. Okay? So this is a very powerful way for us to see down in the high-speed behavior of what our software is doing. Okay? Logic analyzer. So learn how to use it. Okay? Learn the modes of triggering. Okay? All right. All semester we're going to use a debugger that's built into the IDE, and that happens to be a joint test action group debugger. And so things like single step, breakpoints, memory windows, registers, I/O registers. The debugger gives us a very powerful suite of tools called JTAG. Okay? And that's built into our Launchpad and runs in our IDE. All right. We'll define a piece of software that we add to our program for the purpose of debugging as an instrument. Okay? There's lots of ways in which we can do it. I've already told you you can't have the print statement, but if you were to use a print statement, it would be a debugging instrument, because you put the print statement in there. Its purpose is not to run the system, but to debug. Some compilers have this concept of assertion, and assertions get run at runtime, and you will get an error, for example, if x is greater. X is supposed to be greater than 1. You'll get an error if it's not greater than 1. The one we're going to do all semester, and I'll ask it on the first exam, I'll ask it on the second exam, I'll ask it on the third exam, and those of you who have known the printf statement or the output statement, this is essentially the same tool, except it runs on an embedded system and it is minimally intrusive. Okay, so anytime you would have been inclined to use a print statement, we're going to dump. A dump is an array, obviously of finite size, and an index. And if there's room in the arrays, I'm going to save something. Right? This is the same information I would have printed, but I'm going to save it in my array. Okay? Now I could print out, I can dump variables, I can print I/O registers, and I can print time. Okay, so for instance, if I set up timer 1 to be a down counter, I could actually dump the time, which gives me both the data and the I/O registers. Okay, so this aspect of dumping is something that I want you not to do just in Lab 2, but Lab 3 and Lab 4 and Lab 5 and forever and ever. Okay, one of the cool things about a dump is these results here can now go in your report, in your documentation, that this is what I tested. This is what happened when I tested it. Okay, so this becomes a permanent record when you have to write reports on the behavior of your system. Okay. All right, another software thing where everybody loves a flash and LED. And the question I want to ask, is my program running? Is this thread being executed? What I'm going to do is add an extra GPIO pin, set it to an output. Set it to an output, hook it up to an LED. Right? Hook it up to an LED and flash it. It'll mean something. Okay? So again, this is going to be a minimally intrusive. Because the time to execute this line of code is well under a microsecond. Okay? Now I'm going to use, as we talked about before, I'm going to use bit-specific addressing, so this output to this pin is both friendly and has no critical section. And we'll talk about critical sections in a subsequent lecture. Okay? So the question is, if the light is flashing, my program is running. If the light is not flashing, my program has crashed. Okay? We all love flashing LEDs. Now, sometimes the program either runs for a long time, or you have a sense of when your program is behaving badly. Okay? When your program is behaving badly. And so we can, rather than create millions of entries of dumping, we could establish some kind of filter, some kind of condition that says, well, in this case, if port A, bit 5, is high, then it behaves still silly or stupid, or that's where my bug occurs, when port A, bit 5 is high. So I'll filter my dump on that condition, whatever that condition is, because I'm debugging my code and I know what works and what doesn't work. And this filter will greatly reduce the amount of entries into my dump arrays by filtering it. But again, it's minimally intrusive because the execution of this is, the time to execute this code is going to be well under a microsecond. Okay? And that's why this is still minimally intrusive. All right, I've been talking about it. I should have defined it. But intrusiveness is the degree of perturbation caused by the debugging itself. All right, it's essentially the Heisenberg principle for debugging. Okay? To run the debugger, to run the test, may or may not slow down, change the behavior that I'm trying to measure. And as we saw last time, if I take a scope or a logic analyzer and I add it to existing pins, it's completely non-intrusive. It has no behavior. Okay. Now, the things we just did, dumps, monitors, and assertions, take a little bit of time, a very small amount of time, and we'll call that minimally intrusive. As a matter of fact, we can actually quantify the intrusiveness by looking at two things. Okay. We'll define delta T as the time to run the debugger, the whatever instrument we have. And then we'll take T as the time between running. Okay? So for instance, if I call dump every 1 millisecond and dump takes less than a microsecond, the level of intrusiveness is, less than 1 in 1,000, right? 0.1%. And we'll define small numbers like this as minimally intrusive. Now, if you stop execution and start single stepping, because all the hardware events are going to keep running, as we mentioned before, the print statement, if you were to even have one, would be highly intrusive because they're very, very slow. Okay? So we want to focus in either on non-intrusive or minimally intrusive debugging tools so that I can test my real-time system. All right. We defined earlier, debugging is performance and functional. And the idea here is if I take an interrupt service routine and I toggle a bit, let's say PA5, I take another interrupt service routine and I toggle PA4, and I take my main program, and inside my while loop, I toggle PA3. Then on my logic analyzer, I can then look at PA5, PA4, and PA3. I could look at them as a function of time. This is called a profile because it's telling me what software is running, right? That's the what. And the when that software is being run, that's the time axis of my device. So I'm going to be toggling pins. I'm going to be toggling pins in my code that, again, not part of, these are minimally intrusive debugging instruments, not part of the system, but part of the debugging or performance debugging to verify the timing behavior of my system. Okay? So in summary, we defined intrusiveness, which was the measure in which the debugging instrument, the time to run the debugging instrument divided by the time between invocations of that. If this is a very, very small number, we're going to call it minimally intrusive. We defined two steps. We defined the idea of control and observability. Stabilization is another name for control, is how do I set my inputs? How do I set what functions get called? And then the second is observability, which would be a dump or a memory window. If other debugging techniques if I have a 1 kilohertz interrupt, I could test it at 2 kilohertz, that's acceleration. If I have a 1 kilohertz interrupt, I could vary the rate. I could go from 10 kilohertz to a half a kilohertz and making the system more variable. Stressing is knowing what will break and trying to run it beyond specifications. Coverage is the range of input cases you're going to do. This whole idea of testing is a complete discipline in itself. But as you get more mature, you will develop more sophisticated ways to debug. And you remember, you want to keep your job? Learn how to debug. And that's how you're going to keep your job. Okay, see you next time.